All right, y'all, welcome to Unit 2, the atom. If you would, get out a periodic table. If you don't have one, I've got a stack of them up here, but you should have them. Everybody, please get out a periodic table, or you're welcome to come grab one from my pile up here. For those of you at home, they've already copied down this slide. Pause the video and copy it down, please. In the video yesterday, you were introduced to a variety of scientists that went from basically the world not believing that there were atoms because that was an insult to God, to getting to the point where we are now that we know that matter is made up of these indivisible particles that make up everything. So you were introduced to some of the scientists, but you won't be tested over the scientists. Instead, what we're going to focus on today is the structure of those atoms. If we were to go as teeny tiny as we could go into what makes up you and all matter around you, what do they look like? What are they composed of? You copy down this table. These are called subatomic particles because sub is going to be going slightly smaller than whatever it is you're talking about. So these are the smaller parts of the smallest thing, the atom. Protons, neutrons, electrons are the particles that I need you to fall in love with. And there's a bunch of stuff that you need to know about them, especially how to count them, as you'll see will be our primary focus today. But I'd like to go through some of the stuff on the table that you copied and tackle some of this stuff. So, in a nutshell, if I were to draw an atom, the very center of that atom would be called the nucleus. Anything I write on the whiteboard, you write, right? I'm sure that you know that. It'd be silly not to write something the teacher writes. Okay, so just like a cell, the center of an atom is the nucleus. Inside that nucleus, we've got two particles that live there. We've got neutrons that live in there. They have no charge. That's written in your table though, right? The fact that they live in the nucleus with no charge is both on what you already wrote. What's the other particle that lives in there? The protons, right? Because you wrote it on the table. All right, so there's also these positive protons that live inside that nucleus. Zoom in. I should have drawn it bigger. Sorry, people at home. Those are positive P's and neutral N's. Anyway, you'll see that the symbols I'm using match the symbols that are on the table that you copied. So that's part of the basic structure. Now, it's also important to know that these protons and neutrons that are in the nucleus are the only particles in an atom that have mass. If you look on the mass column there, you'll see that it identifies protons and neutrons. Not only do they have mass, they have about equal masses to each other. So what does that mean? All the mass of an atom lives inside the nucleus. So that's a good conclusion that you can draw. There's going to be other stuff in an atom happening out there, but that's not where the mass is. Because of the three particles we're going to talk about today, only two have mass, and they're both in there. So that's the nucleus. Now, the other particles, or rather the other particle, but there's going to be several of them, they live in these circles. Now, the circles are called orbitals. You wrote that down on their table, but you're not going to be charged for that until Unit 3, because guess what Unit 3 is called? Electrons. Unit 3 is just titled electrons, so it's a whole unit about electrons. But we're going to talk a lot about orbitals when we get to the unit after this one. But it's these circular pathways where electrons live. So here's my exciting electrons that are on the outside of the atom. This is kind of an oversimplified rendering, but it's what I need you to know for intro, all right? 3 particles make up the atom, 2 inside the nucleus, and 1 spinning around the nucleus. Does the electron have mass? No, because the table says it doesn't, and you know that all of the mass of an atom lives in the nucleus. So this is the basic anatomy of an atom. If you look at the last column of that table that you wrote down, you'll notice that it says if changed. This is an important column, but I want you to understand what the heck I'm talking about. What that's talking about is, well, what if you removed, don't do this to your picture, just watch for a second. But what if you removed one of the protons? What would that do to this fake atom that we drew? No, we're not doing any exploding, all right? It would change what the element is. It turns out that the number of protons, as we're about to discuss in depth, gives the element its identity. So if you were to remove a proton, the element that you're looking at up there would change to a different element. All right, well, what if you were to remove a neutron instead? What if instead of removing that proton, I had removed a neutron? That's at the bottom down there. Well, that would form a different species of the same element. It would change the mass because neutrons have mass, right? We removed a mass particle. But because the protons didn't change in my fake theoretical here, the element would stay the same, but the mass would change. That's called an isotope. We have 2 lectures over that next week. Actually, I might move that to Friday, Monday. I'm still thinking. And finally, what if you change an electron, all right? And this could be adding, I'm removing, you could also add one. That would change the charge. We're gonna talk more about that at the end, but I just want you to know what that last column's referring to. It's talking about taking an established atom and altering the numbers that are there. More on that later. What I really want to spend the majority of the class focusing on is the column that says to calculate. You see that? One of the things, or the primary skills that I need you to be able to do, is if I give you an element, I need you to be able to tell me how many protons, electrons, and neutrons it has. So I need to train you how to do that. You can read from that column, but I'm going to make sense of it for you. So keep that in front of you while I go to another slide. Find potassium on the periodic table. Find, my friend, I hate that round. I can make a trash can from here. There's no way, right? I hit one of you in the face, I'm sorry. Oh, let's get off the table. Oh, that has a chance. All right, find potassium on the table. And what we're going to do is count the protons, electrons, and neutrons that are possessed in potassium. So go ahead and read back on your table with me, and let's see if we can make sense of this. In order to count the number of protons, it's equal to the atomic number. Now, inside a square on the periodic table, there are 2 numbers. Do you agree? It's important for you to know that the atomic number is the dude up there, And the one down here is the mass number. Atomic number's up top, mass number is on the bottom. And if you want to add a side note that might be helpful to you, you could mention to your brain that the atomic is always smaller than the mass. It has to be. If you're interested in that fact, it might help you later. The atomic number is always smaller than the mass number for a given element. Well, let's see if you've been listening. How many protons does potassium have? 19. Because the number of protons is equal to the atomic number, and potassium's top number is 19. The number of electrons, according to your table, is equal to the number of protons. Now, I know that sounds weird. Sir, why didn't you just say that's equal to the atomic number also? Because I want you to understand a relationship here. You see how electrons are negative and protons are positive? Well, the elements on the table are neutral. What that means is, for every positive you have to also have a negative so that they cancel each other out, right? If I give you $1 and then I take $1 away from you, how much money have you made or lost? None, right? Because I gave you a plus and then I did a minus and it all canceled out. That's the idea, is that potassium doesn't have a charge. For potassium to not have a charge, pluses and minuses, same number. How many electrons, therefore, does he have? 19. So these dudes will be the same number as long as there's not a charge. The neutrons are the only ones you have to actually think about in this case, because the neutrons require an arithmetic. If you look at the rule, it says it's mass number minus atomic number, but let's talk about why that makes sense. Look here. What are the only two particles that have mass? Protons and neutrons. That means that the mass number that's in the bottom of the square is the protons and the neutrons together, right? So if you were to take that mass number and subtract the atomic number, which is the number of protons, then what would you be left with? Just the number of neutrons, right? The masses, both of them together, all right? So that's why it's not, oh, you subtract those two numbers for some reason. That's why, is that this number is protons and neutrons, all right? So just subtract that number, which is that number, and you'll be left with neutrons. Now, I know it's a decimal, and we're going to talk about why in our next lecture, but round it. If you round potassium, it rounds to 39. What is 39 minus 19? 20 neutrons. And cool, you've counted them. You try one. I want you to do the same thing I just did, but do it for carbon. Count the subatomic particles of carbon. Let's go get some help. Let's go talk to cluster 5. C3. Hey, 5-3, you want to share your numbers with us? And then the walls start to bleed. It's really creepy. Yes, carbon is super Satanistic. But yeah, 666 in this case. So they can all be the same because carbon's atomic number is 6. We know that these two values match each other unless there's a charge, which we'll talk about later, right? And then the neutrons is this minus this, which for carbon is 12, that is 6. 12 minus 6 is 6. How are you doing? Now, unfortunately, real life elemental samples don't come directly from the table. They come in two other notations, we call them that. If you go and I was to find an elemental carbon just existing in the planet, it wouldn't have a mass of 12.01 like your table says it does. It might have a different mass, which I'll elaborate why later. But because of this phenomenon, there are two other notations I need you to be able to count subatomic particles in. The good news is that even though I'm about to change that part right there up, I am not going to change the rules up. So as long as you know that he's atomic number, he's equal to protons, and he requires subtracting, then you're going to be good for the day. But let me show you what the other notations look like. Nuclear notation. All right, make a big deal about that phrase because that's what I'm showing you. All right. This is nuclear notation. If you were to summarize the difference between reading it off the table or looking at nuclear notation, how would you summarize the main difference in the way it looks? It's flipped, right? The numbers are just swapped. Now the mass number is up here and the atomic number is down there. But even if you got confused on that, you know that the mass number is always the bigger of the two, right? So as long as you know that, when you run into this versus me asking you off the table, then you should be good. The mass number has to be bigger because it includes the number that is the atomic number, right? Because the mass includes all the protons. Anyway, so yeah, the numbers are flipped, but that's the mass, that's the atomic, and then it makes the next part hopefully very easy. In order to find the number of protons, it's equal to the atomic number, so what will it be? Anybody? 12, right? Atomic number's on the bottom. So this sample of magnesium has 12 protons. How many electrons does he have? Also 12, because our rules state that these two values are currently equal. And let's go over to cluster 5 again and talk to C2. Hey, 5-2, can you give me a neutron count for this sample? Fourteen's correct. It's funny how being put on the spot can make anything just unenjoyable to answer out loud, right? Yeah, 26 minus 12, 14 neutrons. Same rules, slightly different format. Are you still cool? Do me a favor and find magnesium on your periodic table. Find magnesium there. I want you to compare the numbers on the periodic table that the magnesium square has to the values that are written on the screen or behind me. Somebody yell out the difference. The mass is different. He pointed out that looking at these two values for magnesium on the periodic table, that the number on the table doesn't round to 26. What does it round to? It rounds to 24. Why is your teacher so stupid that he wrote the wrong number up there? All right, I didn't. It's an isotope, which I'm going to charge you for what that means in the next lecture, all right, because it's a big concept. But here's what I do need you to understand. Look here. For any particular element, the mass number is variable. Different species of magnesium on planet Earth have different masses. But what's not variable is the proton count. Do you see how the proton count of 12 perfectly matches what's on the periodic table? Because what's true about protons from the very first slide? Protons give an element its identity. You already wrote it down. Magnesium always has an atomic number of 12. That can't change. But magnesium's mass number can be variable. With that in mind, let me show you the other notation. Hyphen notation is what you're writing. Hyphen notation. What element is that? Plutonium. Very good. I'm glad you all memorized your elements. If you compare hyphen notation to an element on the table or nuclear notation, you'll notice that there's an entire number missing. All right? The reason that not only does hyphen notation have a number missing, but it's also the most common notation that you see, is because one of those two numbers that you've been given in the other ways that we've looked at it can't change, which means there's no reason to show it to you. Which number cannot change, the atomic or the mass? The atomic. The atomic number for plutonium never ever changes, but the mass can't, which means the only number that's really worth showing you is the mass number. Because you can always go look up the atomic number on the periodic table. It never changes. But the mass number can change, so it makes sense that I show you the mass of the plutonium that I'm talking about. But now the rest of the counting stays the same. This is pronounced plutonium-243 is how you would say it. How many protons does plutonium-243 have? 94. How did they come up with 94? It had nothing to do with the number 243. Instead, they went and found plutonium on the periodic table, looked at his atomic number. How many electrons does plutonium-243 have? 94, because these two numbers are the same unless there's a charge. Yes? No, because you won't have partial particles, so it'll be a whole number of protons plus a whole number of neutrons. How many neutrons are there, speaking of? 149. Now, for the first time, you use the number 243. 243 minus 94 is 149. Y'all, listen, I lose so many of y'all here. If I give you hyphen notation, you must use the mass that it gives you, not the mass on the table. It might be the mass on the table, but that doesn't matter. If an example is showing you a mass, that's the mass you use. Because what is plutonium's mass on the table? It's 244, which is not 243. If you were to use 244, you would get a different neutron count, and you'd be wrong. Think I can trick you on one? Let's give you an honors example and see if you can impress yourself. I want you to count the subatomic particles of him. All right, let's see where all the brainiacs be at. Let's go over to cluster 2 and talk to C3. Hey, 2-3, what's the proton count? Just the proton count. This is vanadium 52 plus 2. What is it? 23. Do y'all agree or disagree? Yeah, because the protons are the atomic number. The atomic number is not shown here, not in hyphen notation. But if you look on the table, vanadium is 23, yeah? Now, I'm not going to draw a card for these next two because I don't want, this is kind of inherently confusing. Let's go to neutrons, though, because neutrons is what we've been doing. Y'all, this right here is a charge. It's not saying 52 plus 2, right? It's the charge of the ion. It's positive 2. So the mass is 52. Anybody have a neutron count for me? 29. Neutron count's 29. Why? Because 52 minus 23 equals 29. Same thing we've been doing all class, yeah? All right, focus, because man, you don't like this next part. The charge is positive 2. Positive 2. How many electrons do you think there is? Somebody shout. I heard a 21 and a 25. What do you think? What's the charge? You know what that means? If it's positive, that means that when there's the same number of pluses and minuses, it's neutral, right? So if it's positive, overall, there better be more what? There better be more protons if it's positive. Now, I can't change the number of protons, right? You can't be, oh, well, then maybe there's 23 electrons and then just 25 protons. No, because if there was 25 protons, it would be manganese, right? Because protons give identity. If it's vanadium, that has to be the proton number. But the electrons, you can change them, and vanadium stays vanadium. So the answer must be 21 because there are 2 more pluses than minuses, making it positive 2. This is called an ion. You already wrote that down. Don't worry. It's in the opening table on what happens if the electrons are not equal to the protons. let's talk about this altering of particles a little bit. How much time I got? Still got 6 minutes. We're good. People at home, this is going to be the slide that we're looking at. We're going to do those examples separately. All right, let's take a look here. Ooh, F19 and writing that's probably way too bright. What element is that? Yeah, fluorine. All right, let's see what we want to do to it. See, this is called modifying atoms. Let's do some stuff to him. Fluorine 19, it says we want to remove a proton and add 3 neutrons. All right, well, let's get our count first. I know that fluorine 19 has 9 protons because his atomic number is 9. There's no charge, so he's got 9 electrons also. The neutron count is what? 10, because 19 minus 9 equals 10. Yeah. That's fluorine 19, but look what this says. It says remove a proton. How many protons will there be if we remove one? There would be 8. And it says add 3 neutrons. How many neutrons will there be if we add 3? 13. So the question becomes, what is he if those are his numbers? All right, so there's the first idea. Do you see how the protons changed? Protons give identity. We call this transmutation. Whenever one element turns into another element, it happens in nature, right? Radioactivity, that's what's happening, is elements just flat out turning into other elements. It's cool. But now we are element 8. What is element 8? He's oxygen. All right, that's a dash. What is the mass? Remember, this number right here in hyphen notation is the mass number. What is the mass of this oxygen? What is it? No, that was it. What was it? It's 21. Because right back to the beginning, all of the mass comes from the protons and the neutrons. Protons plus neutrons is mass number. And you can prove it, right? To get to neutrons, it's this number minus that number, right? What's 21 minus 8? 13. You see, they're all talking to each other. You just have to have a grip on what the numbers mean. Hey, is there anything else interesting, though, about the way these numbers are communicating? You see how the protons and the electrons, they're not the same. The moment they're not the same, there has to be a charge. Who's winning, the pluses or the minuses? See how there's one more minus than there is plus? So he would have then a -1 charge. You don't have to put the 1. If there's lack of a number, it's assumed 1, but whatever. You can put -1. But he would have a negative charge because there's one more electron than there is proton. So the answer from this change, oxygen 21 with a negative, charge.